right, here are the recitation solutions for Friday, April the 24th. So here we've got a large spinning wheel rotating at angular velocity omega. You can think of this as, um, if you're trying to imagine what we're dealing with here, imagine a solid bicycle wheel with the brake pads located somewhere toward the middle. So here is our wheel. It's rotating around its axis at some angular velocity, and we press two brake pads against it 2/3 of the way out from the middle. So if this is the center line, this distance here, which I haven't drawn quite to scale, is 2/3 r. So when we squeeze it with these brake pads, each brake pad exerts a normal force F sub n. And this applies a frictional force, which opposes the rotation. So there are going to be two frictional forces here. Each has a magnitude of the coefficient of friction times the normal force. So when you squeeze something with brakes, friction happens and slows it down. So it slows down the rotation by applying a torque. And we know that, so our strategy for the rest of the problem, let's go ahead and outline it. So we're going to find the angular acceleration using our expression for the net torque. And then, so if we're relating the acceleration, the angular acceleration, to how long it takes to stop, we can use angular kinematics. Because this angular acceleration will be constant, so omega final is omega initial plus alpha t, and we're going to find the time. So using this expression, so the torque from each brake is going to be the distance from the center times the force. So the net torque will be, let's see, there are two brake pads times 2/3 r times the force that each one applies, mu Fn. And we can set that equal to the moment of inertia times the angular acceleration. So combining terms, I have 4/3 mu Fn times r equals, so the moment of inertia of a spinning wheel is 1/2 mr squared. Well, the radius here, whoops, no, I'm right. 1/2 mr squared times the angular acceleration. So now we can find alpha. Here, alpha is going to be 8/3 mu Fn. Let's see, when we're dividing by r, one of the r's cancels, divided by mr. Let's see if the units come out right. A normal force has units, so coefficient of friction is dimensionless. So the normal force has units kilograms meters per second squared, and we're dividing by a kilogram times a meter, giving us units of 1/second squared. Radians per second squared are the units of angular acceleration. So we did that right. Now to find the time, I know that, well, the final angular velocity here is 0. So I have 0 equals omega naught plus alpha t, so minus, oops, forgot the minus sign there. That just means that it's accelerating in the opposite direction of omega naught, minus 8/3 mu times the normal force over mr times t, telling us that t is let's see, going to be 3/8 omega naught mr over mu f sub n. Let's look at this value and see if it makes sense. So it takes longer if it's more massive, if it's larger in diameter, or if it was spinning faster. And it doesn't take as long if the coefficient of friction is larger, so if the brakes are stickier, or we squeeze the brakes harder. So that makes sense. Let's look at the value of, the value of 8/3. Let's see, yes, we got that legitimately. So we've got a factor of 1/2 on the right. Yeah, we got a factor of 2 on the left, so that is correct. Okay, now we go to another problem with a kitty trying to push over a cup of water. So what's going to happen here? Well, let's think about cause and effect. So the kitty's claws are adhering to the ground on the left. So we're going to choose our pivot here, so we don't need to think about the force that the kitty's claws apply. Yes, it exists. Yes, Reese has to hold onto the ground with some force. We'll label it F claws, but we're not going to worry about it until the end of the problem. But there are two forces that matter a lot. So Reese's weight pulls him down like this. So this weight is just going to be mg. And so Reese doesn't fall, well, because Reese's leaning up on something. Well, Reese's leaning against the water. So there is a normal force going this way. My arrow tool here. There's a normal force from the water. And that means that there is, if the water is going to stay stationary, that means there's also a normal force this way, pushing back on the water by Newton's third law. And the water will spill off the pedestal, it will shift. This moves if the normal force is ever bigger than the force of friction, the maximum force of friction, which is mu s times the mass of the cup of water. We'll write that as m sub w times g. So let's just go ahead and get some symbols here. This is the length of Reese. This is the mass of Reese. This is the height of the stool. So in this problem, I haven't given you a step-by-step solution guide to the thing. This problem, I want to see if you could figure out how to do this on your own and figure out what's going on. So we have another clear diagram here. I put this here so you all could have something clean to write on. So that means I need to reproduce this here. So these are the forces that act on Ricci. And we already decided that this falls if the normal force is at least as big as, well, bigger than, mu s mass of water times g. So we realize that when we do all of the torques, we're solving for the normal force. Now, I'm going to calculate torques a different way in this problem. Remember that torque is either the perpendicular part of the force times the radius, or the force times the perpendicular part of the force times the radius, or the force times the perpendicular part of the radius, or Fr sine theta. And just to demonstrate that approach, I'm going to use it here for this problem. To do that, we're going to need to know angles between the radius vector and all of the forces. So the radius vector is this one. It's along Ricci's body. I'll draw it in bright green here. So it's this vector along Ricci's body. So we need to know two angles. We need to know this top angle, which I'll label as phi. And we need to know this bottom angle, which I'll label as theta. These are the angles between the radius and the forces. Now, in order to get those, I don't actually have any angles given to me, but I do know the length of Ricci and the height of the stool. So that lets me determine that this angle here, which is also phi, so let's see, phi will be the inverse sine, because it's, I know the opposite and the hypotenuse. So this is the inverse sine of the height over the length, and theta will be the inverse cosine of the height over the length. And we'll just leave it in terms of phi and theta and plug those things in later. So now, let's calculate the torques. I know that if Ricci is going to be stationary, the net torque is 0. So the torque due to gravity, let's see, that one's going to be negative. Remember, clockwise is negative, counterclockwise is positive. So minus mg times the radius, which is L over 2, times the sine of the angle, sine phi. And then I have the torque from the normal force, so plus F sub n, the thing I'll ultimately be solving for, times L. Oh, that's not phi, that's theta. Because remember what I want, this angle is always the angle between the radius vector and the force vector. So continuing, FNL sine phi. So if all that's equal to 0, now let me label all of these pieces, first of all. So this is the force, this is the radius, this is the sine of the angle. Likewise, force, radius, sine of angle. So if all that's equal to 0, doing a little bit of quick algebra, this tells me that the normal force is, let's see, so my L's are going to cancel. So that's going to be 1/2 mg sine theta over sine phi. And, well, now I know how, I have an expression I found out a bit ago to relate that to when it falls. So to find the mass of the water, I have mu s mwg equals all of that. So mu s mwg equals 1/2 mg sine theta over sine phi. I can cancel my g's. Notice I can't cancel my masses. One's the mass of the cat, one's the mass of the water. So the maximum mass of the water that Reci can tip over is going to be m sine theta times mu over 2 sine phi. All that's left here is to now put in what those angles are. So I have expressions for them up top. Let's see, so theta is the inverse cosine of the height, which is 75, over the length, which is 90. So theta is, I have to say in degrees in Google Calculator. So theta is 33.5 degrees. And phi, I don't need to type things in again because those two angles are complementary. So let's see, this is going to be, they add up to 90, so that's going to be 56.5 degrees. So finally, putting all of these values in to calculate the maximum mass of the water, I have 1/2 times 10 kilograms times the sine of theta, which is 33.5 degrees, divided by 2 times the sine of 56.5 degrees. I'm getting something that I don't think is right. Oh, I forgot to, no. So this tells me MW max is 1.65 kilograms. Okay. Let's think if this makes sense. So we have a 10 kilogram cat able to tip over water that is 1.6 kilograms. Yep, I see my error. This mu, again, this seemed too small. So I'm always going back and checking my work. So let's look at this expression and let's see how you could have identified my mistake, because I messed up. I messed up my algebra because I was going too fast, and it's always a good idea to look at your expressions and see if they make sense. So this tells me that Reci can tip over a heavier cup of water if he is heavier himself. This tells me that he can tip over a heavier cup of water if he is leaning on it harder, because of the angles. You can kind of think about how those go. But the one I messed up is the coefficient of friction. This tells me that the larger the coefficient of friction is, the larger the cup Reese can tip over. And that doesn't make any sense, right? You'd think that it would be easier to push something over if the coefficient of friction were smaller. So the smaller the coefficient of friction, the larger the thing he can tip over. Always think about if your answers make mistake, or if your answers are right, if your answers make sense. I didn't do that. I didn't think if my answer made sense, and I made a mistake. So that means that when I type these things into Google Calculator, the 1/2 should be in the denominator, which conveniently cancels that factor of 2 down there. And then I get a more sensible result, which is what happens when you think, of 6.61 kilograms. So this is a really important, anybody who's watching this video, this is a really important lesson in humility, right? I've taught this class a bunch of times. This has been an exam problem in the past. I've seen this problem before. I wrote this problem, yet I made a mistake solving it. And I'm the professor in the class. So it is incredibly common for people doing calculations in science and engineering and so on to make mistakes. You will make mistakes in your career as a scientist or an engineer. The important thing is to have those safety checks in place to look at your answer and say, does this make sense, in order to catch your own errors. So yeah, looking at this now, this is more sensible. So make sure you do that. And we had all that conversation about science process. When you're working in a team with other people, make sure that the way that you can conduct your business with other people, the way that you interact with your team members, also has safeguards in place to catch your own mistakes and to catch mistakes of other people and to let other people catch your mistakes. Otherwise, you wind up with things like NASA flying very expensive space probes into the surface of Mars because somebody messed up a unit conversion. That was a couple $1,000,000 down the drain because somebody messed up converting kilometers to miles or something. So that's my soapbox. Last recitation solution of the year. And I'm going to go post these on YouTube.